Okay, I think we'll begin. Welcome, everybody. My name is John Perdiculius, and I'm with Compuplast North America. And this presentation is done in cooperation with CMT Materials. And we'll be talking about the applications of simulation in thermoforming. So during the presentation, we're going to be demonstrating a bunch of different case studies and problems that were addressed using simulation and solved. And we're going to focus mainly on one product, which was plug assist the container with APET. So first of all, I'd like to address what you can do with simulation. Well, it can help you select the type of thermoforming process, whether you're going to do positive forming, negative forming, with or without an assist. It can help you select the polymer material that will give you the best uniformity for a particular product. It can help you select the tool material and the plug material that will help you to achieve the best product uniformity and material distribution. You can predict thickness distribution in your part. You can predict if a web or wrinkle is going to form and address that before you've actually cut any steel or wasted any material. You can determine the total sheet deformation or stretching, and this has implications in determining the effective image distortion. If you are pre-printing your sheet and you're concerned with how an image might look after the part is formed, using the simulation software, we can see how that image might deform. We can look at the stress distribution in the product, and the stress distribution may have a potential problem downstream under the product's working environment. And we can also study the cooling time to give us an idea of the efficiency or the potential line speed that we can achieve for producing a certain product. And the next step really is optimization. Once you see a particular problem, a very thin area or a web or wrinkle, you might decide to modify the part to be able to produce that product more easily. Or you might want to modify the tool design to help correct for any perhaps you have a very tight radius. You might want to change the radius in the part and modify the tool design accordingly to avoid any very thin areas. One of the major areas that simulation and optimization is used is in plug assist design and optimization. Several applications of this. We'll also demonstrate this here in this presentation, but it's a major area where the assists are optimized, designed, the type of material is selected to help achieve a more uniform product distribution thickness. Another area is sheet temperature optimization, particularly with larger parts where they do pattern or zone heating. You can use the simulation to determine the initial heat distribution or sheet temperature distribution that you need to achieve the most uniform final part thickness. And of course, selecting the initial sheet size and thickness can be determined and optimized through the simulation. So let's talk a little bit about the thermoforming process. So here's an example of what we call positive forming. We have a male tool which is underneath the sheet, and you'll see when I show the video, the tool goes up through the sheet line, and then the vacuum comes on and pulls the material down into the details of the mold. Now, throughout these simulations and the results, you'll see blue represents a thick sheet area, and red represents a thin area. So once again, I'll play that. The tool moves up, and then the vacuum comes on and pulls the material down, and you can see the thickness distribution by the colors. Now here is positive forming with an assist. Now note that the sheet gives top priority to the sheet is given top graphic priority, so it appears to be above the assist here. But this bar you will see when I start the animation is definitely above the sheet. And so what's going to happen here is the sheet's going to pre-blow, and then the tool is going to move up, but the bar is going to stay in place and prevent a web forming across here. And you're going to see more about this later on in the presentation. But once again, you can see that the top areas up here that don't stretch much are thicker, and then the red is down in these corners where the material stretches the most. Now here is negative forming with an assist. Once again, the sheet is given top graphic priority, so you see it here as being above everything, but in fact, the actual cavities of the tool are above the sheet, and we have an assist below the sheet. And you'll see when I start playing the animation, the assist pushes the material up into the cavities, then the vacuum comes on and pulls the material up against the cavity surface to complete the forming. I'll show that one more time. The tool pushes the material into the cavities, and then the vacuum comes on and pulls the material up against the surface. And again, red is thin. You can see the corners tend to thin out more, and whereas the bottom centers tend to be a little bit thicker. And the software has quite a bit of flexibility and functionality. One example of this is you can have independent tool movement if your equipment allows. So in this case, we have our cavity under the sheet, our different colored tools above the sheet. And you'll see when I start the animation, the one tool will stop sooner and the other two tools will continue, and then the vacuum will come on and complete the forming. And we can see here that we have a very thick area at the bottom of this section, meaning that perhaps this tool engaged a little bit too much and we want to adjust that, or maybe even adjust the shape and dimensions of that tool to help get rid of that very, very thick area. So just one more time, this tool stops first, these tools continue, then the vacuum comes on and completes the forming. Now, as I mentioned earlier, once we understand the deformation of the surface, then it's relatively easy to apply an image onto that surface and see how that image might deform. And one of the first applications of this was in Halloween masks. And here you can see a multi-cavity tool with one image put in just for demonstration. And when we show the animation, you'll see how the tool stretches the image and then the vacuum comes on and pulls the image down to give it a more human appearance. So I'll show that again. Here's the initial image, some sag, the tool is pushing down, and the vacuum comes on and pulls the sheet up and forms the figure to a more realistic appearance. Now, one of the most important properties of performing an accurate simulation are the material properties. Because the polymers exhibit both viscous and elastic behavior that is time-dependent, we must use a time-dependent viscoelastic mathematical model to describe this behavior. And the TSIM software uses the KBKZ model for calculations. This is probably the most widely accepted model because it is one of the most accurate ones with respect to mimicking the behavior of polymeric materials. Now, the way we obtain data for this model is we need to do stress-strain deformation experiments in which we take the material and we stretch it slowly and measure the force required to stretch it slowly. Then we stretch it a little bit faster and measure the force required to stretch it, and then stretch it even faster and measure the force required to stretch it over time. And when we do this and then we fit this data to a mathematical function, the KBKZ model, and now we have a continuous reproduction, basically, or mathematical function of the behavior or of the sheet with strain relative to stress. So in other words, if we stretch the material quickly, we know how much more force it's going to take than stretching it slowly. We also have to do this at 3 temperatures. We recommend the typical processing temperature, and then that minus 10 degrees C, and then that minus 20 degrees C. And this way, we can encompass the vast majority of the temperature under which the material is actually formed. So we have the effect of temperature and the effect of strain on the stress in the material. There are basically 3 ways to characterize your material. One is a test developed in cooperation with IKP Stuttgart, Germany, and Accuform, the developer of TSIM, which is a force deformation measurement, which is generally the preferred method. There's another test that can be performed at Data Point Labs in the USA. This is a lubricated squeezing flow experiment, which provides data that can be used to fit to a KBKZ model, but it's still not as good as the IKP test, but it's still acceptable. And then the third way is to reverse engineer the material properties based on performance data. So if you are actually forming a part with that material, what we can do is we can pick the closest material in the database to that material, run a simulation, compare the results, and then modify the material behavior, either make it more viscous or less viscous, or more elastic or less elastic, so until we achieve the same results in the simulation as you see in the physical part. And this can be done while one of these other tests are being prepared, so that you can get started on your project. So, what can you study? Well, the effect of the material is one area that you can investigate using the simulation. Here we show a plug-assisted cup, and we're showing, you can see here, we're showing 1/4 of the geometry in the sheet. And this is something that's often done during simulation, is we take advantage of any type of periodicity or axis of symmetry so that we can minimize the amount of calculations that need to be done, and thereby get a faster solution, or get a more finer solution in a reasonable amount of time. So you can see here we're simulating 1/4 of the geometry, and what we're showing in this graph is the thickness versus arc length. Now we use arc length as opposed to X, Y, or Z because you can see here at the top, position A, pretty much all those points along this line are going to be at the same Z position. So by using arc length along this line, we can maintain a graph along the actual length of that line. And so here you can see the effect of using a viscoelastic material, which is the dark line here, as compared to the thickness distribution along this line for a purely viscous material, shown with a light blue color, and purely elastic material, which is shown with this orangey color. Now, the differences here, you can see how they change based on what the behavior of the material is. And this is what I was talking about, the reverse engineering of the material function, was that we actually form this cup, we measure this thickness, so we have a physical data points on this graph, and then we adjust the behavior between purely viscous and purely elastic so that we can match what our thickness distribution is in our experiment. And this way we can reverse engineer our data, our material file, and then use that for optimization or on our next project where we're using the same material but perhaps a different size, different shape tool, and a different plug. We can study the effect of the plug material via the coefficient of friction. Basically, that's how TSIM determines what plug material is used, in that different plug materials have a different coefficients between them and the polymer. And the coefficient of friction is a relatively difficult parameter to obtain, because you need to do it at the temperature at which the material is being formed. And the coefficient of friction is highly sensitive to temperature, so it is a rather complex parameter. But we know, even through experience, that depending on the type of plug material you pick, you can have a very different distribution in the part. Now, for this particular plug shape, we see the range of distribution in thickness for a friction coefficient of 0, which is essentially full slip, up to a friction coefficient of 100, which is certainly full stick. And here you can see that when it's full stick, the plug will push the material up to point A, and you should have a very thick area at point A, almost as thick as the initial sheet. Whereas if the material slides on that plug, it can stretch along that surface, it gets thinner at point A than it was originally. And then you have the variation through the part. And of course, the plug design certainly affects what these results will look like. Here we're studying the effect of the final plug position. In other words, how far is the plug penetrate into this cavity before the vacuum is activated. And here you see the dark blue, the triangles are a 40 millimeter, so the least amount of engagement. And then the vacuum comes on, and because we've only pushed the material a small distance, less than halfway up through the cavity, the material has to then stretch as it pulls to reach the point at A. You can see we have our thinnest material at point A, all right, and then our material gets gradually thicker and thicker as it moves up to point B. And the most uniform wall thickness, again, the most uniform wall thickness from point A to B, you can see, is when we have the greatest engagement. In other words, we've pushed the plug 90 millimeters into the cavity, and in this case we have a higher thickness at point A and a more uniform thickness all along that wall, and then an increase in thickness as we get up to the flange of the cup. And finally, we can also study the effect of plug size, or for that matter, plug shape. In this, just to make things simpler, in this example, we've taken a plug and we've reduced it by 80% and reduced it by 80% again, and used it to form at the same depth, the full depth, 90 millimeter depth. And you can see the difference in thickness distribution that you're achieving with the different plug sizes. Now this can get even more elaborate, as I'll show in the next slide, in terms of what plug shape, what radius, in terms of optimizing the distribution of the material for your part in the way that you want it. So as an example of this, here is a video of a simulation of two plug assist designs. On the left, we have a typical rounded nose plug, and when you see the forming of this, you see it pushes the material down, and then the vacuum comes on, and we can see that the thinnest area is down in the corner of this cup, essentially where the material has to travel the furthest to reach the surface. Now, these results have been scaled to highlight the thin areas. So we specify a critical value of, let's say, 0.5 millimeters or maybe 20 thou or 15 thou. And then we show everything above that in blue, and then we focus on the thin areas where they are. Now we keep the same scale, and we use a different plug, which is a slightly larger diameter, and it's a concave bottom. You can see here at the bottom of this plug is concave. And we go down to the same distance, and then we pull the vacuum, and now we see a very different thickness distribution. In other words, the thinnest part is actually the vertical wall, and the bottom corner is a little bit thicker, and certainly thicker than what it is on this side. So here you can see two plug designs, and of course any variation in between can be tested ahead of time without cutting any steel or wasting any material, and this optimization can be done very quickly and very efficiently in the simulation. So now we're going to move on to a few case studies that have been that we've selected here that demonstrate some of the capabilities of the simulation and some of the benefits that you can see. So the first one is a sheet temperature optimization, and this is mainly for large parts. This example was for a large sign that this person wanted to produce. And one of the concerns here was that when they were forming with a uniform sheet temperature, the material would get very thin in the corners, and they would risk potentially cracking them. So they had to pick a thick starting material. You can see here 4 millimeters starting material, and consequently they waste a lot of material in the center of the sign here to achieve the required thickness in the corner. Through the software, we can determine the optimum temperature distribution for a given range. Here we give it a range between 150 and 160 degrees Celsius. And the software gives us a temperature distribution. Now in this example, we're not looking at thickness here, we're looking at temperature. So the blue area is 150 degrees C, and the red areas are 160 degrees C. And when you form, excuse me, when you form this part, you get a more uniform distribution in the final part. And here we're looking at thickness. The blue is thick and the red is thin. And in fact, the customer was able to achieve his minimum required thickness was 1.1 millimeters. And they were able to achieve this with a sheet that was less than 2 millimeters thick. So they saved more than 50% on their initial sheet thickness, which is a considerable savings in their material costs. And the difference in thickness between the corners and the center was greatly reduced. The maximum thickness in the center is now 1.6 millimeters through doing the pattern heating. So here's the comparison of the two results. The next example is a plug depth optimization study. In this case, the client was making these transportation trays. I don't know if they were for muffins or some sort of food product. And they wanted to optimize or determine the optimum plug penetration depth that would give them the best thickness distribution for their tray. And so a series of simulations were run using the software. The thickness were measured from points 1 to point 20 as shown in this image here. So point 1 would be right there, and then point 10 would be right here, and point 20 is over here. And you're going to see the thickness distribution along these points for the plug going 1 millimeter from the mold bottom. This is essentially the bottom position, and then plus 10 millimeters, 1 centimeter, and then plus 2 centimeters, and then plus 3 centimeters. So we're going to have 4 penetration depths, and we're going to show the graph of the thickness along positions 1 through 20 for those 4 depths. And what they found was that by doing this experiment, they wanted a result that was somewhere between the 1 centimeter and the bottom, and they ended up with an optimum final plug position of 5 millimeters from the bottom of the mold as the one they would use for their production, which gave them the best stiffness of the part, and it worked best in that application. This was a problem that somebody was facing with what they call incomplete forming, and you saw this earlier in the presentation, or a variation of this, where a refrigerator liner was being formed using first pre-blow of the sheet, and then when the tool engaged, the vacuum came on and completed the forming. Now again, here you see that we're taking advantage of the symmetry down the center of this mold, and you can see that the problem here is the area between the refrigerating and the freezer compartment that does not form completely and doesn't pull in. So we get a web being formed in that area, and the question is, how do we get rid of it? And if you do the simulation before you build any tools or try anything, you can foresee it ahead of time and correct it. And the solution, of course, is the assist. Here's the thickness distribution. Here's now the thickness with the critical thickness areas. You can see that we have blue 1.8 millimeters as the maximum thickness, and anything below that is shown between the yellow and red spectrum. And we can see that this is the thin area in here. And this is the scale adjusted to 3 millimeters, 3 millimeter scale. So by adjusting the scale, we can focus on what areas are below our critical values. And this is a thickness plot across the center line of the tool. This graph is showing the thickness along the arc length, and these crosshairs here are right here, this position. And you can create graphs in any cut location direction you want to investigate the thickness distribution of the part. And here is the solution. We have a bar that is used to essentially, this bar remains in its position, but it prevents the material from forming that web. And you can see here is the pre-blow with this bar. Again, this bar is above the sheet, and it's holding the sheet, preventing it from forming that web across these two areas. And then the vacuum forms, and you don't have that web to contend with. I'll play that one more time. And then you can plot your thickness distribution again along the sheet, and you can see this time that the thickness drops down in the flat area, and determine if this is an acceptable result for you. And if not, You can make adjustments either to the tool or the forming process or even your initial sheet size to correct that. This next example deals with a motorboat housing. Once again, we take advantage of symmetry and we just use half the tool for simulate half the part. And this part requires a draw box, a vacuum draw box, because it is a relatively deep draw. And again, we simulate half of that. And you'll see here from the simulation that we pull the material into the vacuum draw box. Then we move the positive tool in, and then we reverse the vacuum to form the part on the tool. And you can see the formation of these two webs in these corners. Once again, we pull the material into the draw box, move the tool in place, and then reverse the vacuum to pull the material onto the tool. And the problem is we have these two webs or wrinkles in the part, and they're above the trim line, so this is unacceptable. And so when you're looking at a problem like this, the people involved may come up with 4, 5, 6 ideas on how to solve it. And instead of trying those experimentally, we can use the simulation software. In this case, they wanted to use these corner pieces, which they refer to as web catchers. And of course, there's a question of how much of the material do you want to take out of play. Well, the exact position and size of these web catchers can be determined via virtual trial and error using the simulation. And then when you go to build it, you have a greater confidence that by removing this material from allowing it to be included, then there's no excess material to form a web or wrinkle on the part, and you end up forming the part properly by taking that material out of play. And so here is the final part distribution. Now we adjust the scale to show the critical thickness. The critical thickness here was, I think, 3 millimeters. So we adjust the scale to show everything that's below 3 millimeters. And you can see here that that falls below our trim line, which isn't a concern because all this material below the trim line gets recycled back into the process. And we know our product will have an acceptable thickness all the way through. The next study here is plug selection. As I mentioned, you have a couple of people looking at a project. They'll come up with several ideas. Here we want to form this cup, and we end up with 3 plug shapes that are proposed. How do we know which plug shape that are we going to test or try to achieve the desired thickness distribution? We simply set up a simulation and run each one of those through the same conditions and look at the results and evaluate the thickness distribution that's achieved by each one of these different plug shapes. And so here we can see with a thickness distribution, all of them at the same scale of 0.13 millimeters minimum to 0.8 millimeters maximum. And we can see the different thickness distribution that the different plug different distribution that results from the different plug shapes. Here we can see that we have a very thin sidewall. Probably and again, we'd have to look at the exact graphs of the thickness for each one of these, but we can then decide which one of these plugs gives us the best distribution, and that's the one that we will work with, or perhaps try to optimize further. This is now the scale's been adjusted to 50 thou, and this from 0 to 50 thou. So now we focus more on the thinner areas, and we can see the very different thickness distribution that's achieved with these different plugs. So this one gives us essentially a more uniform, thinner area down to the bottom half of this plug. This is thinner in the corner and thicker on the edges, and this one is much thinner in the corner and much thicker on the side. So very different distributions. And from here, you might get ideas to modify these plugs further and run additional tests for optimization. The final case study here deals with a part quality improvement and cost reduction. And it was part of a European project for optimizing the thermoforming process and the mold manufacturing. And there were many people involved in this, and one of the lead companies was Accuform, the developer of the TSIM thermoforming simulation software. And in this case, the objectives of the main forming company, which was Sabert, for making food containers, was to optimize the production of this container. And here's the mold, and here is the plug assist shape that was used. And in fact, they had a 2-up cavity for the trials, and they were using the high-tack plug material provided by CMT. So they set up a design of experiments with the parameters that influence the plug, and they had the initial conditions and then the variations for each condition plus minus. This works out to this 16 experiments, which to do physically is, and with repeats, of course, is a lot more effort than setting up a batch run in TSIM to run these overnight and then analyze the results of these 16 runs in graphs along cuts using the same cut for each analysis. And they found that there was the existence of these 4 groups of thickness distribution, which were based on a couple of main parameters. And these 2 major parameters were the sheet temperature and the plug penetration depth. So they said, okay, let's focus on these, but now let's also focus on the plug. So first of all, here we have the simulation results with sheet temperature. And when the sheet temperature goes up, the side elongation goes up, and the bottom corner thickness goes up. That's what they found on these experiments. And the plug penetration depth goes up. The side elongation goes up, the bottom corner thickness goes down, and the part center thickness goes up. So they needed to optimize that position. But this time they added also the optimization of the plug shape, and that was to make the plug, here you can see it's the external surface is made smaller by 8 millimeters or larger by 2 millimeters. So they adjusted the plug size. And then they ran a series of experiments here where they had the two cavities isolated, different to the 2 temperatures and the 2 penetration depths. And they found that when they ran with the smaller plug, they had smaller side elongation. Faster one was possible, but they had less plug mark, this one. With a sheet temperature of 135 degrees C, they had higher thickness at the bottom corners, which helped the part thickness, and less plug mark or freeze off. And then the plug penetration of 55 millimeters, they were able to run faster. They had less change in the corner thickness and lower side elongation. So by running these studies, they could optimize the part thickness distribution, and this effectively resulted in the possibility of using a thinner sheet to obtain the same quality or same stiffness. And the conclusion of the experiment was using the simulation software to study the parameters and the dimensions and the influences, they will be able to improve the part quality. They can improve the cycle time by using a smaller plug. There's a new plug made. and they could reduce the cost by using a thinner sheet. And the cost reduction was from 0.5 millimeters to 0.45 millimeters, which was a gain of 9%. What they found was in the year that they were running this part, they could have saved, they produced about 2.5 million parts. They could have saved themselves 2.5 tons of plastic. This was their estimate. 12.5 tons of plastic. This was their estimate. And they could have had this overall cost reduction in their part because they had less material cost, less forming cost. They had a little bit higher mold amortization because they had to adjust the tools and take into account the simulation, but the mold optimization is a small portion of the total cost. So the total part savings was 9% lower. So finally, I'd just like to finish off with a little demo so you can see the software in action. I'm going to show that right here. So this is the TSIM thermoforming simulation software. And here what we're going to do is we're going to set up a project where we're going to thermoform a cup with a plug assist. And the first thing we do is we define the project setup. We put in some name for the programmer or simulator and the job number. And then normally we specify our initial grid size. So we click on New Grid, and it opens up our grid window, and then we define the dimensions of the sheet that we're going to use, the thickness that we're planning to use, 1.5 millimeters, the initial thickness of the temperature of the sheet, and the number of elements, because this is a finite element simulation. We then create the sheet, and you'll see here the elements. These are the triangular elements, and we save this sheet with some name. Now, we normally start with low number of elements to have a fast initial simulation. We add this sheet to the project, and now we move on and add the tools. Now, the tools have been imported, developed in a CAD program, and basically STL file format is the format used, and they can just be selected and brought into the project. This is the assist now, you see round bottom assist. And the next item is the process control. So now we're going to create a new process control, and we're just going to simply save it, and then with some name, and then add it to the project. We save the process control, and we go browse for it, and we add the process control to the project. And now, when we edit that process control, sorry, we save the project at this point. And now, when we edit the process control, we see the two tools in their initial position, and we see the spreadsheet here, which gives us the timing, the vacuum, and the tool position. And so now we're going to adjust these parameters. So let's say in 200 milliseconds, we're going to have the tool 2 moving from 0 to 111 millimeters. And then in 500 milliseconds, so over 300 milliseconds, we're going to pull a vacuum of 50 kilopascals upward. And the tool is going to remain where it is. So we're going to get rid of the unneeded lines. So you'll see here that the simulation is 500 milliseconds, or half second of the real process. So once we've defined the process control, we simply, so we have to make sure also that tool 1 is an upper tool and tool 2 is a lower tool. And then we can save the process control. And finally, we need to add a material. So we pick a material that we've added to the database. From the database, there's about 20-25 materials in the TSIM database. And the last item is the friction coefficients and heat transfer coefficients. Now these are just going to be set kind of almost randomly, because this particular simulation is relatively short. But here you want to probably, in a real example, you want to pay more attention to this, because they can have an effect on your process. So basically we define the heat transfer and the friction coefficients and we add them to the project. So we've defined all the items that we need to run a simulation, and now we simply save it, and we can go and review, see all the items that are in there. That's the tool, and you'll see the assist here, and our process control, of course, that shows the steps in the process and when the vacuum comes on and how much, and the material file, and finally the heat and friction data, heat transfer and friction data. Then we solve the project. So here you'll notice that this is real-time kind of solving of the project, and you'll see the thickness changing on the part. We've turned on the dots here to show the contact of the element nodes with either the tool in blue or the assist in green. At some point here, the vacuum comes on here, and you pull the material to finish the forming. So here you can see the final formed part, and there you can see the elements of the sheet. Now notice that it's not a very smooth result because we used a relatively low number of elements. So now we go in and we use the automatic refinement option to increase the mesh density. Then when we close the project, we can save this as a new sheet or rename the old sheet if we want. So here we're going to rename it Sheet Refined. And now we're going to open the project and simply select the more refined sheet. So here we open the project and we browse now for the sheet, and we select the sheet that's more refined. Now we simply, you see the sheet overall dimensions are the same. It's just that we have many more elements in that sheet which can better follow the curvature. Now we resolve the project, and the simulation will take a little bit longer because it's performing more calculations. You can see the calculation steps at the bottom left of the screen, and the timing, the milliseconds of the simulation. And as we define this, the plug will move 111 millimeters, at which point the vacuum will come on and pull the material off the plug and up against the tool surface. Now you'll see at the bottom left here, you'll see that that happens after the 200 milliseconds that was specified in the process control. So there, now the vacuum comes on and pulls the material out, and finally it's formed. And now with the more elements, the sheet has effectively more flexibility, and it can capture the curvature better. Now we make the sheet solid here, and we show the elements, so you can see here the finer mesh. And again, thickness is represented by color. Blue is thick, red is thin. But we can also make a cut, and we'll show you here the cut window. And we'll make a cut along the x equals 0 position. And you'll see the graph is linked to the graphics window, the crosshairs of the position is shown. Here we switch to the Y, and you can see symmetry will make it virtually identical result, either X or Y, and this justifies using symmetry for the simulation. We can then take our data from our cut window, copy it to a clipboard, and take it to an Excel file and make a spreadsheet of various cuts with different materials, and that's why some of the graphs in the presentation were made. So here we study the effect of raising the vacuum pressure, making it a little faster. We simply change that number, save that process control, and then rerun the simulation with a different parameter. And we can do the same thing with the friction coefficients, study the effect of different materials. We can increase the friction coefficient or decrease the friction coefficient and see what effect that has on the distribution, as well as having several plugs in the process to study the effect of the different plug shape or geometry or diameter, whatever you want to study to optimize the distribution and achieve the distribution that you want. Once you finish the simulation, you can also export your formed or deformed mesh, the final part shape, out for structural analysis and study the deformation or crushing test, let's say in ANSYS or Abacus or some other finite element stress analysis program. Here we're showing the bounding box that kind of shows the size of the sheet. And here you can see at 200 milliseconds, now the vacuum comes on and completes the forming. And again, we can increase the thickness and take a look at the results. And over on the right, you can see the thickness scale through the system. So that's it for the demo. There's our contact information if you have any questions about the simulation or anything about the presentation that was made today. Please feel free to give us a call or send us an email. So with that, I'd like to thank you very much for your time and your attention today. And we'd also be pleased to answer any questions if you'd like to just type them in to the question window. Okay, well, it doesn't look like there's any questions there. Once again, I'd like to thank you very much for your time. And as I mentioned, please feel free to contact us at your convenience, and we'd be pleased to answer any personal questions about the software or any, maybe even do a demo on one of your products. If you care to share the tool with us and some material information, we can run a demo analysis and show you the benefits of using the software to help optimize your process on your particular part and tool shape.